We've done IPv4 addressing. We talked about IPv4 subnetting, and it becomes a kind of a big deal in the subnetting because we're out of IPv4 addresses. We're still using them, and if you look at your ipconfig all on your Windows machines and your Linux machines, and probably maybe even on your tablets. In my tablets, some of them one of them I think will do an IPv6 address and one won't. We're using this concept called dual stack, and we're using dual stack because some sites still are using only IPv4 addresses. And what will happen is and I'll try a ping here, if I ping, and then this one I think esaa.com, the place that we're using for those things, gives me an IPv6 address. Ping net, it gives me an IPv4 address. This one only responds to IPv4. This one responds to IPv6. In the dual stack, if IPv6 is available, it's going to be used. It's a much more proficient, efficient, and secure protocol. So that is the one that we really want to use as much as possible. And we talked about, I said about 4.25 billion addresses, IPv4 addresses. That's a lot of addresses. But all of the publicly available addresses have been issued. Down at the bottom there, the IPv6 340 undecay, and I told you I didn't even know what that was until we started looking at this. That 340 and all those other numbers after it is how many IPv6 addresses are available in the IPv6 address range. Probably not going to run out for a while. Might they eventually run out? Absolutely, because we keep putting more and more and more devices on the network. I read things like, I don't know, somebody was saying, I guess it was the course that I was taking, that a washing machine or dryer or something had an IP address. A thermostat has an IP address, and you guys may have some of those devices. Refrigerator has an IP address. Yeah, we have all of those things. Keep in mind as you do those, if you add those, or if you already added those, the security of the protocols. Because once somebody gets into your network, the Internet of Things, once somebody gets into your network, they're on your network. And that is how Home Depot got hacked. They got hacked through the environmental controls to do those. IPv6 addresses are in hexadecimal. Let me put a blank slide in here, and we'll try to do a little scrawling here on hexadecimal. We talk about it and all the other things and kind of assume that everybody knows how to do hex, and that may in fact be the case, but let's do it again just in case. Hexadecimal goes, and hex is 16. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go A, B, C, D, E, and F for the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 0 to 15, it gives us 16 stuffs. And again, 16 stuffs, 16 things. 0 represents something. And in the network addressing, the IPv4 addressing, it represented the network address, where the host bits were all zeros. The way that we would change something to or convert something to an IPv6 or a hexadecimal number, if we had something like, we won't take something very big, let's take something like 80, we would still convert it to binary. 1, 2, 4, 8, 16, 32, 64, 128. So is there a 128? No. 64? Yes. 6, right? 6, and then 1, 16, is that right? 0, 1, 0, 0, 0, 0. The way that we would now convert this to hexadecimal is divide the 8-bit into two parts, two 4-bit areas, and then renumber this one 1, 2, 4. So this number 80, we have our what? 4 here plus 1, 5, 0. And you can check that to see if that is in fact the correct. The process write it in binary, divide it in half, 1, 2, 4, 8, 8 and 4 is 12, 14, 15 is the max when we have all of these things. 15, if we have all ones, 15 is going to be F, 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 on down the line. Let me do one more and let's see if I really make a mistake here. Let's see if we can get some other things out here. Let's go to 206, and I don't know what it's popped into my head for no apparent. 128 we got, so we'll subtract the 128, 8 and 8, 16, 78, 64 we get, minus 64, 8, 8, 4, 14, I think, is that right? 0, 0, 1, 8 and 4 is 12, 14. So this one, yeah, this one's going to be a little bit better. We've got the 8 and the 4 is the 12. So 12 we go here, 10, 11, 12 is going to be C. And then, 8 and 4 is 12, 14, CE would be the hex representation of 206. Hexadecimal is just simply a shortcut method to write binary with those things. You can do a hex converter, but why we want to do that is so you can see where the numbers are coming from, because when we do EUI64 we're going to have to do some changes to this thing. Blank there. So binary to hexadecimal, and this is the clicky version of what we just did. Convert the decimal number into binary, then split it into groups of 4. The decimal 255 for the 2, and this one's going to be FF. All ones, it's going to add those up, it's going to be 15. 15 was going to be the F1, and 128, 1, 0, which is going to be what, 8, 1, 2, 4, 8, 8, 0 for that one. You can do all of those things. What we wrote, or what I scrawled, the decimal to the hex, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F for the representation of these things. Again, this is something that we talk about, and I don't know that we ever actually, except here, say, hey, this is the way you do the conversion. It's just like, okay, you should know how to do that. And no, you shouldn't know how to do that until convert each group of 4 into binary bits, and then into the decimal, then the hexadecimal for these things that we just did. The hexadecimal 15 here, 15, 15, FF. This would be F, yeah, F, and then FF would be the representation of this thing. 80, E0, F0, and F5 would be the conversions here. Again, if you want to practice this, I think that the Windows calculator, the scientific calculator, will do decimal to binary, and decimal to hexadecimal, decimal to octal if you really want to do that also. So an IPv4 address 224.1.87.122 would translate to the following. 224 is going to be E0, the 1 is going to be 0, 1. 87 would be 57, and 122, 7A. So if we wrote it in hexadecimal, it would be the E0.01.57.7A. The reason we're doing this is IPv6 addresses are written in hexadecimal. That's the way they're represented, because they're a 128-bit address. 128-bit address, if we're going to write all the ones and zeros, that's going to be a pretty long string. And it's going to be split just like the IPv4 address was into network address and host address for these things. A full address of the examples, and let me do a couple of things here. The abbreviated address is the example, and these are kinds of things that you might be asked about. What we can do is always drop the leading zeros. So we can drop all the leading zeros in this thing. A little bit of a simplification. This is called zero compression, I think is what we're going to call this. Zero compression. Or leading zero compression. Yeah, leading zero compression. So we're going to compress the IPv6 address into something that's a little simpler down here. We go 2001, and they didn't drop this one. They could have. It could be written as DB88. 0, because we have to have at least one something here, except when we get to the next one here. 56, 0, and then A, B, C, D, E, F, 1, 2, 3, 4 to do these things. So the leading 0 compression, we can drop the leading zeros. Makes writing it a little bit simpler. The other thing that we can do down here is if we have a string of zeros, regardless of how long it is, we can replace it one time, and once being a key word here with a colon colon. So if I had something like 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, 0, 0, 0, 0, I could replace that whole string with a colon colon. The reason you can only do it one time is the system's got to be able to calculate how many zeros you actually replaced in this thing. So in this one, in the abbreviation down here, 2001, and again we could drop this leading 0 and just make that DB880. We bring that 0 down, 56, and then we use the colon colon for this string of zeros, and everything else we're going to write out. A little bit, some things that can be used to make writing them a little bit easier, because when you start doing these things, especially if you try to put static IP addresses on stuff and static routes, it is a pain, because you've seen the typos that I make. So it is, any help would be great for me. IPv6, 128 bits, 16 bytes, 8 hexadecimal blocks. And if you look at these things, 1, 2, 3, 4, 5, 6, 7, 8. The first 4, typically /64. The first 4 hex blocks are going to be 32 bits, are going to be the network portion. And then we're going to have a whole bunch of addresses, host bits that are assigned to us. And I kind of, as you know, move back and forth, and sometimes a little bit early for the others. But you may have looked at your ISP granted you, if you signed up for it, configured your router for IPv6. I'm going to bring mine over here. And as soon as it gets connected here, see, I have an IPv4 address here, but I go to internet connectivity and to the IPv6 portion, and it says delegated prefix 2603-6008C30331B2 : colon colon means everything else is zeros, /64. They've delegated, and delegated prefix is the term that's going to be used for the network portion of this thing. So this is the delegated prefix, or the network that I can use on my home network. So I've got, 32 bits worth of, or I've got 64, excuse me, I've got 64 bits worth of, I did the multiplication wrong earlier, 64 bits worth of addressing that I can use. And I can subnet these things too by simply moving the CIDR notation, and these things are written in CIDR notation. I have a LAN, and we'll look at what these are. Remember, FE80. But this one is my wide area network. This is the one that goes to the ISP. It's a 2605, different than the one that they gave me to go onto the internet, or to assign IP addresses on my devices. So we have this thing, 128-bit address, 16 bytes, noted by 8 hexadecimal blocks, and that's where I ate 16-bit blocks, and I was doing 4 times 8. I got my 8s and my 16s backward. The bit on the extreme left is the highest order. High order bits are always going to be on the left, and the bits on the right are always going to be low order bits. So the highest to the lowest, high order to low order bits can be abbreviated for convenience. We can drop the leading zeros. Leading zero compression is the term that's going to be used. And we can replace 2 or more groups, or 1 or more groups, 2 or more groups of, and the groups here would be the hex groups, I think, for here. 2 more groups contain all zeros with a colon one time, and that's called zero compression. Zero compression where we use the colon for a string of zeros, leading zero compression where we simply drop the leading zeros. Leading zero compression we can do as many times as we want, because the system knows, the stack knows that that we have these 16-byte groupings here to do these things. 1, 2, 3, 4. So if I drop it and I've got a 0, it knows to that for the addressing, and this would be the network portion for the addressing, that it has those zeros in front of it. The URLs are kind of a little different, because if we use IP addresses for a URL in IPv4, we just simply put the IPv4 address in. For IPv6, the URL goes in brackets. And when we do this, a colon 8080 here is the port number that would be used, and then the page index.html that we would go. But this would be the address of the resource of the web server. This would be the port it's going to use. 8080 is a pretty common Windows proxy server port that will go, so instead of 80 or 443, 8080. Again, a pretty common Windows proxy server port. So the address prefixes for this thing, the leftmost bits denote the subnet, and then the number of bits to the subnet is the prefix length, the /64 that you saw that my ISP had assigned me. The syntax is the IPv6 address and then the / prefix length. Again, prefix length is going to be the number of bits, just like in IPv4, the number of bits that are in the network address. So what the ISP assigned to me before it times out is, this is the network address that I can use, and it is going to be a routable network address. There's not going to be any private IP addresses in IPv6. One of the things that the security people kind of get upset about is they like natting, because NAT conceals our IPv4 addressing scheme. Some, I guess, facts or information about these things. Address auto configuration, and that's what is typically going to be used for these things. I'm going to go and look at try to look at my NIC configuration and show you, yeah, it's kind of like a DHCP, but we don't have a DHCP server. So in it, if I go down here to the IPv6 and go into properties here, it says obtain the address automatically. If I go into advanced, automatic configuration only. What happens in this address auto configuration is dynamically obtains the IP address. It actually creates its own IP address to obtain the address without any physical intervention for these things. Two types: the stateful, which is DHCP, and I know we haven't talked about DHCP, yes, Dynamic Host Configuration Protocol, where we have configured a server that will give us or assign to us an IP address for our devices. That's the default configuration for Windows and Linux, is they're trying to get an IP address automatically from a DHCP server. So this is stateful auto configuration. We have to go and set up a device, a DHCP server, an IPv6 DHCP server. And the host sends a solicitation to the multicast, that multicast address, and FF02. In IPv6, most of the multicasts that we use are going to start with FF02. IPv4, they start with 224. Mostly they start with 224. The multicast address with a source of FE80/10. FE80, we haven't got to it yet, but it's going to be called a link local, or a local address. It's kind of like the PIPA addresses in IPv4. We'll get to those in a minute. If a DHCP v6 can't be found or reached, it reverts to stateless auto configuration, the next one. And in the stateless auto configuration, the router sends the the client the network address. The network address goes to the client, and then the client produces its own, creates its own host portion of the address, so that we have a lot of them. We don't have to have the DHCP server in this case, so that the client, and this is what mine's set up for, the router sends me the IPv6 network address, the prefix, and the system produces its own IPv6 address. You say, well, what if the two of them, what if we have a conflict? There is a protocol, the duplicate address detection, the DAD protocol, which is used before I put the NIC online with the IP address to check to see if there's a duplicate. If there is, we'll generate a new address. There are a lot of them. When we do that, we have the 64 bits worth of them. The IPv6 stateless auto configuration, SLAAC, stateless auto address configuration for these things. A dynamic method of assigning IP addresses that does not require a DHCP server or a stateful server. A stateful server is just a device of some sort that we're going to be using. In the stateful or stateless auto address configuration, SLAAC, connects to the network. The router provides only the prefix of the host IP address, the network portion of the address. Using the prefix, the host builds its own unique IPv6 address, and then the steps that the host performs to generate the IPv6 address are, but to obtain the prefix length, 64, 48 bits, whatever it is. It could actually be longer if I subnetted. I could maybe have a /16 and 64%, 80, I guess would be there if I created subnets, and I can create subnets if I need. Communicates the router with RS and RA, router solicitation and router announcement messages. What's supposed to happen when a device comes online, the router detects that, hey, there's a new device here. Let me announce my presence, and we're going to announce to it the host, the prefix of this network. And it can then generate its own host portion of the IP address. If that doesn't happen, the router announcement doesn't happen, then the RS, the router solicitation, is sent to the routers by the host, which basically says, hey, I'm here and you didn't offer me the prefix, so please send me the prefix. And then it will do that. And the stuff down here, router advertisements, solicited FF02, all IPv6 hosts are unicast. Routers advertise their presence periodically or in response to router solicitation messages. The host comes online, didn't get the router announcement, sends a request to it, and then it does its thing. It builds the IPv6 address using the prefix and the host ID value. This says EUI64. I'm going to show you that mine is not. We'll get to EUI64 in a minute. If it's Cisco, it's going to build an EUI64 address if we specify, and I want to show that. Coming up pretty quick, but extended unit identifier EUI64 uses the MAC address as the basis to build the IPv6 address. But the Windows things, and I tried to determine that mine was an EUI64, and it's not. Ensures that the no hosts are using the same IPv6 address. It uses the duplicate address detection, the DAD protocol. And if it is a duplicate address, it just simply generates a new one before it puts the NIC online. Let me go back to and look at my place. There's a window behind me. I have a hard time seeing one of the screens. Actually, I have a hard time seeing both of the screens. So IP config, and let's do an all. So we get all of this nonsense here, including all of my VMware, my virtual NICs that are running on this machine. But the one that I'm using right here is the physical NIC. The Ethernet adapter is here. It's a Realtek, and I have the MAC address. And then I have the IPv6 address, the 2603, and we have preferred and deprecated and preferred temporary IP addresses. Sometimes individual resources, individual services want an IPv6 address. And the deprecated is yeah, that one's done, but let's wait and see if we need it again. But we have two preferred addresses here. And let's go back to, and it timed out. If you see that address, and I'm trying to make all these things fit here together. What can fit here together is I can copy this. Let's go to IPv6, and the prefix 2603/6008C33, 2603, there we go, 6008C03, 31B2, and then the rest of it is generated by the device, and it's generated a couple of them. The other thing that we have on here, and when we do that, to generate the host portion, if you look up here at the MAC, and the EUI64 uses the MAC address as part of the host portion, it's not even close. There is absolutely no relationship, and I've got more than one IPv6 address on this thing. We also have this thing down here, the link local, which we'll talk about in a few minutes. This is used in the, and the %13 here is just the, it's a Windows thing. That is the interface. We use the FE80, the link local address, for all local communications, because if you go down here and look at the default gateway, it's an FE80 address, and it's a IPv4 address, 192.168.1.1. Again, mostly we have 192.168.1 or 192.168.0 for, unless we change them, and I haven't changed this one. I didn't really see any need to. I guess I could, because everybody in the world is going to be 192.168.1 or .0, so probably can figure out what the internal addressing is. So the FE80 default gateway local device within the broadcast domain for the IPv6, although we're not going to have conceptually the broadcast domain. We don't have broadcast in IPv6. So in the where does all of this stuff come from, try to show the addressing itself. The modified EUI64 automatically generates a unique interface ID. The last 64 bits of the IP address denote its interface ID, and the host generates it by converting the 48-bit MAC address. And I said I wanted to show you one of these things. I've got this set up, and it is kind of a Cisco thing. When I go into this device, and I think it's the one, I want to do a show run to show you the configuration IPv6 address, and I give it the prefix, and this is the network address, ://64, and you notice that's the FE80:1 and then : . Yeah, everything else is zeros. We can do that. I did that just to make this one simple, and then /64, and then tell it to do an EUI64 address. Look at a couple of things. We'll show IPv6, and this is one thing I will show. IP interface brief, and that's going to give me IPv4. If I want to see IPv6, I have to show IPv6 interface brief. And when I do that, I have addresses. I have these FE80s, and they're everywhere. They get assigned automatically by the device, and again, it's going to be a link local. But I have this FA00:1, and then I have an address here. The rest of the address here, the host portion of it, the host portion of the address, 2D0:BC, and one of the tippers that it is an EUI64 address is this FFFE. We split the MAC address in half, add the FFFE to it, and flip. It's called flip the bit, the 7th bit of the MAC address, and let's see. And we show interface fast Ethernet 00. I have the MAC address here, 00D0 on down the line, and if we go back up here, can get both of these on the screen. We have 2D00 instead of 00D0. BC, and then we have the FFFE. Right in the middle of this thing, we put the FFFE, and then we have the A0, AA01. So the difference here is the 0, 0 versus the 2. And that happens because in this first digits, this is going to be what, the first 8 bits of this thing, we flip the 7th bit. So if I do 1, 2, 3, 4, 5, 6, 7, 8, 0, 0 for the hex, and then flip the 1, 2, 3, 4, 5, 6, 7th bit, I'll put a 1 in here, change it from a 0 to a 1. 1, 2, then it's going to be 0, 2. I can drop the leading 0, and that's where the 2 comes from. So the colon says, hey, everything is groups of zeros, and the 2 here, it's not long enough, but I can drop the leading zeros, and that's in fact been done here to get the 2D0. That's the process for converting a MAC address to an IPv6 EUI64. And now we'll go through the slides. And how do you do it? What does the configuration look like? You can put these on the routers if you want to do that, or on the Cisco devices. Again, tried to show you my Windows one. It's not even related. EUI, when we specify EUI64, will generate it using the MAC address, split it in half, putting the FFFE in the middle. Because we have 48 bits, we need to add the 16 bits in order to get to the 64 bits, and then we change the 7th bit of the existing MAC address. And the 7th bit of the MAC address specifies whether it is a locally configured MAC address or whether it is the burned-in address at the manufacturer. I think that when we were looking at some the other day, so this is going to become significant when we get to IPv6, the 7th bit, whether it's a 1 or a 0. You just change, if it's a 1, you change it to a 0. If it's a 0, you change it to a 1. And that's the way that the system generates the EUI64 address. Generates its interface ID by converting the 48-bit to a 16-bit value. The conversion of the MAC involves the steps: dividing the MAC into half, the OUI portion, and then the NIC part, or the serial, or the unique, or a lot of different terms. And I've never seen one that is consistent on what you call the second half, except it's the host portion of the MAC address. First 24 bits and the last 24 bits are used, inserting the 16-bit FFFE between these, and then we're going to flip the 7th bit, the 4B here. The 4, 1, 2, 4, and the B is what? 11. So we have 8, 2, 10, 11. So we're going to change this one from a 1 to a 0, which should then give us a 9 here, I think. Does that sound right? If that is it's at 1, 2, 4, 8, 8, and 1 will be 9. So it should be now, instead of 4B, 4, 9. When we do that, it didn't do the answer, but this would be that's what that one would be. This is just the one that we had, that I had on the that actually was generated for my NIC. If you flip the 7th bit, that's the I guess the tough part. Is it an EUI64? Use the MAC address. The FFFE is going to be kind of the first step in what happens on this thing, and then to check to be sure it's got the 7th bit. You'll get questions: is this an EUI64? Has it been converted? Those sorts of things. And if it has the first portion of the host portion, lots of portions there, is going to be different than the MAC address. We're getting close to, and I guess it's close enough. Let's keep going with the IPv6 address types. The address types here, different ways to classify them. The number of recipients, we have the global unicast. Those are like the public IPv4 addresses. These are the routable addresses. And the ones that we will get inside of our networks, our home networks, our business networks, are going to be globally routable, global routable, global unicast. Anyway, they're routable addresses, which again upsets a number of security folks who got used to NAT, because NAT would then protect our internal IP addressing scheme. So the internal address, the address is going to go on the internet, is going to be the address that is on the device itself. There is no network address translation, no NAT process for IPv6. The unique local are like the old private IP addresses. A couple of names that they have or have had: unique local, and if you look over on the right, the scope, or the link scope, also called the site scope or the site local addresses, unique local addresses. These are routable internally. They can be assigned by the corporation, by the enterprise, and route internally with those addresses. They're not routable on the internet. And the FC there, that's what they're going to start with. They're either going to start with an FC or an FD. The link local is the FE address. FE80 is what you're going to see on if you look in an IP config on your device for the link local address. It's used in a single broadcast domain. It's used on the inside interface of the router, what we would call a broadcast domain. Even though in IPv6 we don't have broadcast addresses, we have multicast addresses, and the anycast and the unicast, all the other ones that we have had. And then the other capabilities here: IPv4 compatibility, IPv4 compatible addresses or IPv4 mapped addresses. Use a concept that the IPv4 address actually becomes part of the IPv6 address. May make things a little bit simpler. And then the scope, whether it's going to be global, site, or link scope. Link scope, the FE80. The link is the broadcast domain, all inside of if we had an Ethernet, would be an Ethernet link. To do those things. And the site scope, the site in this case is not limited to a physical location, but it can, a single site belonging to an organization can be multiple sites now. Originally it was a single location, but it can be routable if you have different locations, like a leader quest does. You could do those things. So it's based on the scope of the application, the link scope, access address, the site scope, global scope, are also interface, realm, admin, and organization scopes when we look at. The global unicast, and you saw mine was 2603, and I think that my address to get to the ISP had assigned me was a 2605 address. But the global unicast, a public IP address used on a single interface, an IPv4 address. That we would use, a public address or a private address. There are no private addresses in IPv6. IPv4 would be the public or the private. But to a single interface, and the example up here is a 2001/BBDB :7777::/48. And if you look down here, the global routing, the global routing prefix is 48 bits, and then the subnet ID is 16 bits. The ISP, and the ISP is the one that assigns these addresses. The ISP assigned me a /64. Your ISP probably would assign you a /64. Lots of addresses, and to me that's just phenomenal. Do I need that many addresses? No, I'm not going to have whatever 2 to the 64th addresses or users or devices on, and I can subnet those if I want to do that. The global unicast are similar to the IPv4 public addresses. An organization that requires a public IP address is assigned a block of unique IPv6 addresses called the global routing prefix. And then, using the IPv6 address within the assigned block, an organization can create subnets. And this 16 bits here, 65,536 subnets. That's a whole bunch of them. And each one of them has 1.84 times 10 to the 19 hosts. So plenty of hosts available, plenty of bits available to do subnetting, because we can subnet these things simply by moving the mask, the prefix to the right, /64 on down the line. Each IPv6 address used in the network is a public address that is unique across the world. There is no network address. And we get that because we have all of this 340 undecillion, that really big number of addresses available. And again, how many addresses are available? One of the things that I read, and you can take all these just for illustration purposes, is that for every human who has ever lived on planet Earth could have 5,000 addresses. And I don't need 5,000 addresses, and you probably don't either, but we could have that. The unique local address assigned to a single interface, unique within an organizational network. They're not registered and they're not routable globally. Similar to the IPv4 private addresses, and they have an FC00:/7 divided into two blocks, the FC00 and the FD00. You'll see both of those is currently not defined. The FD00 has 48 prefixes that can be used. The first 8 bits are fixed, and the hex digits FD and the remaining 40 bits are assigned in a random order. So the unique local addresses, although you see in the literature, it's in the FC00 address range, and most of them start with FD. Remember that we have in that range, we're going to have more than just the FC. So the FC00 and the FD00. The FD00, if you use those, are the prefix that we're going to see with that one. Use subnetting, works the same way as the global unicast. All subnetting works the same way. We have the bits, the /, the CIDR notation specifies how many bits we have in the network portion. Everything else is going to be. The link local address is one that the systems generate themselves. Even if your ISP does not support IPv6 for you, and when we were in Charlotte, the router did that, and I asked them, will I get an IPv6 address? And they said maybe. When we got here, I turned it on, and probably 2 hours later, I had an IPv6 prefix assigned to me with a /64, which means 64 bits, the whole bunch, the 1.84 times 10 to the 19th. Addresses are available to me, but the link local addresses are used in, and back to where I was going, even if your ISP hasn't enabled it for you, and you have IPv6 configured on your machines, it's going to use IPv6 internally. IPv6 is going to be the preferred protocol. We'll use these link local addresses, which are going to start with FE80 in order to, so they're going to be distinguished by that FE80 is going to be on down the line. In the Cisco, if you look in the Cisco stuff, FE80, and then we're going to have some colons or whatever else that we have in here, and we're going to see the MAC address or the EUI60. At the end of that, go back to the one that we looked at this morning, and I think that it will show us that when we go back here, and I guess we can just here, let me get rid of the back up here, the FE80::, and then we have the EUI64 portion that's assigned to the FE80 for this thing. And the other one here that we did, the MAC address, the FFFE assigned in the middle, and then the flip, that's it. Can be used for that, similar to the IPv4 APIPA addresses. In the IPv4 APIPA addresses, the 169 addresses, 169.254 addresses, can only be used internally. I'll drag this back over here. When we're talking about this, the EUI64 addresses would be available, we would have on this interface. They'd be used for communication in these two directions. This one up here, if we had a switch here within the switched network. Here, EUI64. So the EUI64s are used to connect to the adjacent hosts. Everything that could be seen in what we would call a broadcast domain. And I keep saying what we would call a broadcast domain is because we don't have any broadcast addresses in IPv6. We use the neighbor discovery protocol to instead of broadcast, the neighbor discovery protocol, which effectively becomes a broadcast to find all of the adjacent resources. So similar to the IPv6 addresses required on every IPv6 interface, and if IPv6 is configured on the device, it'll generate its own link local address to communicate with all of its neighbors that are within that link. All interfaces in the network can dynamically generate on their own. It's made up of the prefix and an interface ID, and the prefix, the FE80::/10. F is all ones, and E is things. And then the 8's going to be a 1000. The 10 bits go in here, followed by 54 zeros. This makes the address unroutable when we do that. So these are not routable addresses. They're going to be only for communication on that host. In the Cisco host, the EUI64 format is used to generate the interface ID, and we saw that in the simulator, in the packet tracer simulator for those. The multicast addresses, FF00::8, and when you look at these, all these here are FF02. FF02 is a local unicast or multicast address. And what are they? FF02::1, all hosts and routers. So how do you get to be a member of that group? Install IPv6, either on a host or a router. FF02::2, all routers that have IPv6. ::A, EI02::A, EIGRP protocol for IPv6. ::5 and 6, OSPF for IPv6. And then FF02::9 down here, all RIP routers, and this would be RIP version 2 because it's a multicast. RIP version 1 is a broadcast, and we'll talk about those when we do routing. IPv6 address that identifies the many interfaces. We talked about that a little bit yesterday in the subscription basis. How do you subscribe? By either installing it or having the protocol, the service running on the device itself. All IPv6 does not support broadcast addresses. There are no broadcast addresses in it. I was going to go back to my command prompt and do my I would have thought that I do have an FF00:/8, but I would have thought that I would have seen an FF02::1 in that addressing. So we should have those, and those are going to be self-generated for the multicast address, but is configured on the devices themselves. First byte, FF, the host can belong to more than one multicast group, so it can have more than one multicast address available to it. The link local scope multicast address are used to ensure that the packets are sent and the multicast address stays within the range. And again, multicast has never been enabled on the internet. So multicast is within the ISP or within the enterprise itself. To see these addresses used are reserved for the link local scope multicast addresses, and these are going to be the ones within our link within our enterprise. The anycast address we looked at yesterday for IPv4 for the DNS configuration. We had the same IP address in Denver that we had in Houston. To get to one of the DNS servers, that we had, so that you go to whichever one can best serve you, best service you. Closest would be the conceptually the thing that we would talk about. And this one here, we're in Germany and we have a server with an Anycast IP address. They have to be configured as Anycast addresses, and we have US, South Africa, and Belgium. Belgium's going to be closer to Germany, so that would be the one. And then we have the numbers here that represent the cost to get to us. We had a 4, a 3, and a 2. It obviously is going to go to the lower cost to get there. It's going to go to the closest host. And the closest may not be physically closest, but whichever one can most efficiently service us. Some addressing that we can see, the : /128, meaning is unspecified. It's the first address. The number of addresses is 1, and it's one that's never going to be assigned. Default route : the default gateway. The loopback address to me is the only easy thing in here. The 127.0.0.1 is represented by : 1. And it's always going to be up. It's the virtual interface that we would have. These are valid address nomenclatures that we have. I think that, yeah, we're up to a